see, we're going to do number 2. Remember, if you're working on something different, that's fine, as long as it's physics related, but just try to keep it down so I can hear myself thinking and explaining, and those that are working on number 2 can hear me explaining if not thinking. So, number 2, we got this arrow. It's being fired with this force over this distance. What is the speed of the... So, we know, is the kinetic energy of the arrow changing? And I would say yes, because in my experience of firing a bow, it usually starts from rest. You guys agree with that? Yeah. And then it leaves with a higher kinetic energy. So, the question is, how is this kinetic energy changing? Well, it's changing by the string doing work on the arrow. So that's where I would start off with my Y here. It's number 2. And I would say the string does work on the arrow to increase its kinetic energy. So, by that, the amount of work the string does on it is going to increase the kinetic energy of the arrow. And that's probably all I would need for my Y. I may need to show, let's see, yeah, that'd probably be good. I should probably show that I understand what work is, that work is a force through a distance. And I should probably also show that I understand that kinetic energy is the energy of motion. So the main understanding I have to have is this idea that work, the string does work on the arrow and it changes or increases its kinetic energy. But I also should show that I understand how work is done, and the kinetic energy is related, or is the energy due to the object's motion. So I'm going to start right there at my Y, in my how, that the work that it does, and actually for my equation sheet that can be net work, is the change in the kinetic energy of the arrow. So work is produced by force acting through a distance, both those in the same direction. I get my parallels there. Equals KE final minus KE initial, and that's of the arrow. We said that the arrow starts from rest, and if KE is the energy of motion, if I don't have any motion, I don't have any kinetic energy, so that the initial kinetic energy would be 0. I do, of course, it looks like I'm almost ready to substitute in here. I think one more substitution for my equation sheet, the kinetic energy is 1/2 inertia speed squared will do me. But I need to make sure that when I do substitute in for force and distance and inertia and velocity, that they're all in my base units, since they want this in meters per second. And they give me the inertia of my arrow, but they give it to me in grams. So I need to convert that to what's our base units of inertia. Kilograms. They give me my force in newtons. Good, that's base unit. But they give me my distance in centimeters, so I need to make sure that I convert that to meters. So, so they tell me, of course, I've forgotten all my numbers, 95 newtons, that my force is 95 newtons. That my distance is 0.85 meters. 1/2 My inertia, 84. So that's to kilo, so that's 3, so 0.084 kilograms speed squared. So I can divide both sides and square root. Well, the distance, they tell me, on the arrow over a distance. That's the distance. Well, they described my arrow as an 84-gram arrow. They're telling me the inertia of my arrow there right at the beginning. But they're very similar in other directions. And then I would just plug in my calculator and do a little algebra. Right? Let's see. Pull out my calculator. Okay, so let's see. So I'm going to do, let's see, 95 times 0.85. That'll be my work. That would be divided by 0.5 times 0.084. And that would be my V squared. If I was writing this, that would be my V squared. And so my V would be, I took my left side of my equation, and then I realized I wanted to get V squared by itself. So I divided that left side by the 1/2 times 0.084. The stuff multiplied by V squared on that side. But my answer, I need to have square root of that answer. I don't care what V squared is, I want V, and it tells me my V is 43.8 meters per second. Because I divided by a very small number. My inertia of my arrow is very small. So yeah, that's how it came out so large. What's the inertia of your arrow? Correct. How far did you pull it back? Maybe I could be wrong also. Let's try mine. You were wrong? I was right. So, if you need help, need to look at your individual work, let me know. I'll come right over and help. All right, so we're going on to number 1 here. After this one, I'll be glad to come over and help you. But definitely, I'll come over after this one. So we got this spring that we're told that the spring constant is 88 newtons per meter. Remember, that's the description of the physical nature of the spring. How stiff it is, what it's made out of, what its diameter is, all these things go into that K. Don't really worry about what goes into them. Realize that it's a physical description of the spring. Kind of like you would describe like the arrow had inertia. That was a physical description of the arrow. Here's the physical description of a spring. It's a different constant, but it's saying, hey, it's purple. No, it's 88 newtons per meter. They're asking how much work to stretch it from there to here, and they're asking us to use a graph, so we'll use a graph, but I think we'll actually do the calculation by hand rather than calculating it off the graph. But when I do work on it, I'm going to change the amount of energy that it has. So this is number 1 here. And when the work is done, it changes the energy the spring has. Not a great English sentence, but. And in this case, we're changing the position of the spring, so that means we're changing the potential energy of it. Remember, potential energy is due to the position. So, in this case, the work, and I'm going to forget. The work changes the potential energy elastic of the spring. So that's what I'm going to have for my Y. And so, if I do work on it, I change the potential energy elastic. So, exact statement I had in my Y is where it helps me to start off my how. So, let's see. They tell me the K, need the work to stretch it from this to this. Alright, so they asked me for a graph. I'm going to do my graph right down here, this little bottom part. And so I'm going to do an axis. Like we saw when we were talking about it, let's call this X, the distance it's stretched. And this is the force. And this is actually part of my how. Remember, my force is proportional or equal to kx. We had that back when we did thing force. So my graph would look like that. And they're asking me to find the amount of work, let's see, the amount of work from here to here, which would really be that area under here. Okay? I'm going to do it rather than figuring out that area, I'm going to do it mathematically here. But we could just do it by figuring out that area. Break it into shapes that I know how to take the area of, like a triangle and a rectangle. Right? Yes? So, but I'm going to do it over here. Work's what I'm looking for. My change in PE is going to be my potential energy final minus my potential energy initial. Because it's elastic potential energy, my equation for elastic potential energy is 1/2 kx squared, and that would be kx final, minus 1/2 kx initial squared. Anything that I can factor out of those two to combine and maybe to make my life simpler? I can't pull out, no, I can't, because that square is only applied to the x. You're going to have to have brackets around. But I can pull the 1/2 and the k out. We're not, yes, it starts at rest, it ends at rest. So the only work that's being done on it is to change its potential energy, change its position. So I can bring out that 1/2 and that k and leave the x final squared minus the x initial squared. And so now I substitute in 1/2. My K is 88 newtons. 88 newtons per meter. My final X for me is 4.8 centimeters. But of course, I'm going to convert that to meters. So 0.048 meters squared minus my initial location. My initial location is 3.8. So 0.038 meters. Square that. And now it's just a grind with my friendly calculator. So let's see, we got 0.5 times 88, open parentheses, 0.048 squared minus 0.038 squared, close parentheses, hit enter, and I get an answer of 0.038 joules. Let's see if I got it right. Let me double check that I haven't messed up anything before I pause it. 0.038. Yay! Okay, so let me know if you need help individually on this one. Alright, so we're going to talk about number 8. Probably the last one we have time for, but gravitational energy of a cliff diver decreases by this. Also, her weight is doing work on her to change her gravitational potential energy because her position is changing. Remember, potential energy, position, they kind of sound similar. Sorry, am I keeping you awake? Drops of water from a height of this. I'm assuming the water is at a height of 0. Remember, I can place that 0 wherever I want. Determine her weight in newtons. So, what I would have in my Y, number 8, is that her weight does work to change her PE grav. That's a G. And yeah, that would be it. That would be it. So I might want to show that I understand that her potential energy. Yeah, that might be a good thing to have in there also. Sorry. Second thought. Potential energy is due to a force and a position. Yeah, that'd probably be good to have in there. So, right away, work is done and it changes her potential energy gravitationally. Right? So whatever work is done on her is going to cause her PE to go from a final value, from an initial value to a final value. We said that her final value, if she's going from this height down to 0, her final value is going to be 0, right? And you might even draw, happy little cliff. Yay! And you could say, oh, her PE grav down here, will it be 0? Because her height is 0. You could show that. Don't show like work with an arrow. You don't want to indicate that it's a vector, right? It's not. It's a scalar, right? So her work's being done that way. So here's the weird thing you're going to kind of end up with. The work is going to equal negative her initial potential energy. And because that negative doesn't indicate direction. but it indicates that her potential energy is going from some value to 0. So it's changing, it's lessening. So what you can really do is just kind of forget about that negative, that it's even there, because you understand that the work is going to decrease the amount of potential energy she has. So it's changing it negatively, it's reducing the amount, right? You'd end up with a negative weight, which would be kind of strange. But you might look at that and say, oh, that's kind of strange, I'll just forget about the negative. But don't think it's a direction. Be careful of that. All right? So they tell me that 25,500 joules of work is done. So 25,500 joules. I know that this is, please stop kicking the cabinets. They have to last me like 20 years. Oh, is that it? Okay. Remind me at the end and I'll see if I can't type it up. Her weight is going to be mg, so I'm going to leave that. That's her weight. And her height, that's here, her initial height. Ooh, I could change my potential energy if my weight changed. Her initial height is 39 meters. And so now I just solve for her weight, which we know is mg. So that might even be good to put in here, 39.0 meters, and here's 0 meters. And so I pull out my calculator, and I do 500 divided by 39. That's the weight they gave her. 654 newtons. Let's see if it's right before I write it down. No, she's quite massive. It's okay. Cliff divers are tough people. Well, now think about it. How massive is that? That's 65 kilograms. That's not that big, actually, because that's in newtons. So, and in fact, that's one of the arguments of why we'll never go to the metric system, because some people wouldn't want to be told that they're 700 newtons. That would just kind of freak them out.